In this video, we're going to explore halohydrin formation from alkenes. Halohydrins are molecules that have an alcohol, that is a hydrin, and a halogen. Yes, hydrins are alcohols. Remember that when you're taking a biology course and you use a stain called ninhydrin for proteins. There's an alcohol in that. The conditions of this reaction are you need an alkene, you need a halogen dissolved in water. The combination of a halogen dissolved in water is called halogen water, in this case chlorine water. The result is a Markovnikov product. Markovnikov because the electronegativity of oxygen is 3.5, chlorine is 3.0. The oxygen with a higher electronegativity is on the more substituted carbon, tertiary in this case. The less electronegative halogens on the less substituted carbon, secondary in this case. The two groups, as a result of this mechanism going by way of a triangle once again, the two groups are anti in their stereoselectivity. There's a backside attack on a triangular intermediate, which guarantees anti-stereoselectivity. The mechanism will look very similar to our previous 6.1d exploration. We will not be attacking a halogen. The halogen is already reacted with water. We will show that mechanism shortly. But there will be a triangular cyclic chloronium intermediate in our reaction in 6.1f as well. And there will be a backside attack by water, not chloride, by water on the more substituted carbon. So let's start our mechanism now. To start, one of the lone pairs on water will attack one of the chlorines if it has a temporary dipole, which it will. It's a backside attack and the other side leaves. And we generate this intermediate here. This intermediate here is the conjugate acid of hypochlorous acid. It's got an extra proton that HClO does not. This is the electrophile towards attack by the alkene electrons. So this will be taking the place of Cl2. But the mechanism will be otherwise identical. We're going to do our best to mimic this reaction with our new electrophile. Looking at our new electrophile, I know you're tempted to attack the oxonium with the pi electrons on the alkene, but that is never how you neutralize an oxonium. Neutralizing oxoniums is normally achieved by taking an H off of them or attacking an atom otherwise adjacent to the oxygen, which is what we're going to do here. If you use the strong acid of the hypochlorous acid conjugate acid, you will generate a carbocation. That is much slower than generating a triangular intermediate with no octet violations. You might want to review the previous video in 6.1d if that made no sense. Chlorine gets attacked by the pi electrons. Water leaves. The lone pair comes back to the more substituted carbon and makes a sigma bond there. Not happy with the way these arrows look. I'll tidy that up a little bit. So please verify these mechanisms are identical. Pi electrons here attack the halogen. The halogen has a temporary dipole, which is why it was attracted to the pi electrons. This halogen is bonded to a more electronegative atom, which makes the halogen actually feel very positive. So it gets attacked by the pi electrons. The lone pair on this halogen here come back to the more substituted carbon. The lone pair on the halogen here comes back to the more substituted carbon. Water left here because it was attached to the halogen. Chloride left here because it was attached to the halogen. We should get the same triangular intermediate we had here. And I'll rotate it so it's clearer. Here's the cyclic chloronium. Here's water that was formed. I'd also like to point out, not only is water formed here, but this molecule is surrounded by water for one simple reason, and that reason's right here. There is more water present here than anything. Keep that in mind for later. Water, like chloride, has a lone pair which can do a backside attack. And why does it attack the more substituted carbon? Because that carbon spends more time with a positive charge. And the triangle pops open. That was a backside attack. A backside attack on a bond to a wedge chlorine will be a dashed bond to oxygen. We will draw that. The result is this oxonium-containing species, which is the conjugate acid of our final product up here. To make our final product, we must do an acid-base reaction with the appropriate base. And when I say appropriate base, I want the one that is a combination of the best base in terms of pKb and the one that is everywhere, which is water. I told you it was coming up later. Water will deprotonate this oxonium like this, and generate the hydrin, which is an old way of saying alcohol, and that would give us our final product. The oxonium ion loses its H to water. Water becomes hydronium. VicinalHalohydrin is formed. The question now is, why is water a better base for this last step than chloride ion formed way back here? I will answer that in two parts. So why is water a better base for the final step than chloride? Water has a pKb that is 2 units lower. Water becomes hydronium. pKb of water is therefore 14 minus the conjugate acid's pKa, 17. Chloride pKb is 14 minus the conjugate acid's pKa, negative 5. 17 is 100 times stronger base than 19. And the second part of the answer, which is just as important, 2, water, being the solvent, is present in vastly higher amounts than chloride. Let's review our new words, Regio selectivity and stereoselectivity, before we close this video out. Regio selectivity, we'll start with the bottom part here. Oxygen with an electronegativity of 3.5 is on the more substituted carbon than the less electronegative chlorine, which has an electronegativity of 3.0. This is a Markovnikov reaction when that is the case. The stereoselectivity results from backside attack, always giving anti-stereoselectivity because you're coming in 180 degrees away from this bond that you're breaking while you're keeping this bond. So one will stay a wedge, and the new bond has to be on a dash because the water came in 180 degrees away. This is anti-stereoselectivity, very similar to the result over here. Although there was no regioselectivity here because the atoms had the same electronegativity. I hope you found this video on halohydrin formation to be very edifying.